Welcome back, everyone. This is lecture number 8, and there will be only one part to this lecture, hopefully. So we are moving away from the geometry of Greeks, and we're jumping to 1500s, and our next main character, or the character for this lecture, would be none other than Cardano, Girolamo Cardano. He was born 1501, and I think he died in 1572. We shall talk about his book. He wrote a book, and it was all about algebra. As I said before, we're moving a little away from geometry at this point. And the book is called Ars Magna, the Great Art, and it's all about algebra. So we shall talk about a solution to a cubic equation, actually not to a general cubic equation, but to a so-called depressed cubic equation. I'll explain to you in a minute what that means. So let me just write the titles here. This is Cardano's solution to the depressed cubic, or to the cubic. This is taken from Ars Magna, a book that he wrote in, I think, 1545-ish. I'm not so sure about the date. Okay, so what do we mean by depressed cubic? We are seeking solution to the following. We're seeking solution to the following equation, cubic equation, x to the third plus mx equals to n, where m and n are some positive coefficients. So this is called a depressed cubic, because it is missing the quadratic term. Of course, the general formula for a cubic equation would be ax squared plus ax to the third bx squared plus cx plus d equals to 0, where a, b, c, d at this point are assumed to be all positive coefficients. Okay. So we shall state the theorem and prove it. I will state the theorem, or I'll write the theorem rather, in Cardano's words, although it will look a little strange at this point what he meant by whatever he said as part of the rule for solving this kind of equation. It should be mentioned that at this point in time, the terminology was not as it is today, obviously, so it left a lot to be desired. So it may seem very strange, a very strange statement of the rule for solving this kind of cubic equation. Nonetheless, we shall proceed with the proof, and at the end it takes a little bit of work to translate it back to Cardano's words. Okay, it should be mentioned that in his book, Cardano actually supplied a solution to a very specific cubic equation, namely x to the third plus 6x equals to 20. Of course, x equal to 2 would be a solution, as we all probably know. Why there is a need to actually go to such a length to give a specific, or rather write a theorem just about this specific equation. Okay, we will give a general proof to this, a more general proof, more general terms for x to the third plus mx equals to n. Okay, so first I will write the statement. I'll write the statement and then we'll take it from there. So, theorem. rule to solve x to the third plus mx equals to n. By the way, Cardano was a very interesting character, and you should all read in the book something about his life. Definitely is an entertaining read. So let me move on. Here's the statement. Cube 1/3, so cube 1/3 of coefficient of x, of coefficient of x. Then add it, well, add to it, so add to it the square of half of the constant of the equation, half of the constant of the equation. And take the square root of the whole, and take the square root of the whole. Okay? You will duplicate it. Repeat rather. You will duplicate or repeat this. And to one of the two, you add half of the number, you already squared. Okay? And from the other, subtract half of the same. Then, subtracting the cube root of the first from the cube root of the second, the remainder which is left, is the value of x. Certainly looks it looks strange, but what did he actually mean by all this? Okay, so we shall start with the proof. As I mentioned a minute ago, we will talk about a more general proof to all depressed cubes or cubic equations of the form x to the third plus mx equal to n, where m and n are positive coefficients. Okay, so I already drew the diagram, so I don't take time from the lecture. So Cardano actually had a very geometric flavor to this proof. He actually started with a cube, of sides t. So let me just, I'm starting with this cube, let me just name some points. Let this be vertex A, B, C, D, E, F. Let me call this G. Alright, so he starts with a cube whose sides are of some length t. So what he did, he divided the AB, the line AB, which is equal to t, into two lines. Let me call this, or two segments rather, let me call this part L. So first we start, so say we have a large cube, with sides t. Okay, we divide the line AB, which is equal to t, onto parts AL and LB, such that LB, I'm going to call it little u, and LT therefore would be t minus u, such that LB is u, and obviously AL would be equal to t minus u. Okay, here t and u are some auxiliary variables we shall see at the end. So what we do is now we slice the cube with side t into 6 other pieces and consider their value. So what we do is we build another cube with sides u here, and then we build this other cube, I mean the larger cube, within the largest cube. So we have this small cube with sides u, and this other larger cube with sides t minus u. So obviously this will be u as well. Okay, so before I tell you what the sides, oh, not the sides, but what these other 6 pieces are, let's identify some lengths here. So this is also t, this is t minus u, this is again u, this is u, this is t, this is also t minus u, and this is u. So we have this smaller cube of sides u, and we have this other larger cube with sides t minus u. Okay, so we have divided thus the cube into 6 parts. So what are, let me just identify what the 6 parts are. So we slice cube, with side t into 6 pieces. 6 pieces. And consider their volumes. Okay. So what are the 6 pieces? So one would be the small cube with sides u. So small cube with side u, and volume of that would be, and volume what? Volume u to the third. Volume u to the third. Okay, the larger cube, this other larger cube hopefully is visible. I mean, you can distinguish what large cube I'm talking about. That's what I mean. So larger cube with side t minus u, side t minus u, and value t minus u to the third. Okay. 3, we have the slab facing AL. So this is AL. I'm talking about the slab, this slab here. That is right in front, or facing rather the side, AL. Keep in mind what would be the value of this. This is t minus u, this is u, and this is t. So the volume of that, so we have the slab facing AL with volume t minus u times t. So with volume u times t minus u. Okay, we have the slab facing this other, well, let me call this P, facing PC. So the fourth one would be another slab like this, but facing PC is right here, and with exactly the same value, because this side is also t minus u, the height is t, and this length here is also u, just as long as the side of this cube here. Okay, so again we have a slab facing PC with the same volume, with volume ut times t minus u. Okay, the fifth part would be the part that is standing on the top of the small square, which will be this slab here. Okay, the one standing on the top of the small square. So the height of that would be t minus u times u times u. So u squared times t minus u, and that will be the block standing upon the small cube, with volume again u times t minus u, or u squared times t minus u. Okay, and the block beneath the larger cube. So you have this block here right beneath this larger cube. So the sixth part is the block standing beneath the larger cube. With volume well, the volume of this would be t minus u times u. So would be u times t minus u squared. Okay, so our original cube A, B, C, D, E, F, G is made of these 6 other volumes. So the value of our cube, the total value of our cube would be, so our cube, original one, would be t to the third, is made up of adding all these other volumes. So we would have u to the third plus t minus u to the third plus 2 ut times t minus u, because you have two of those, two identical, 2 ut times t minus u, plus this value, u squared t minus u, plus this other value, plus u t minus u, the whole thing squared. Alright, so we'll manipulate this algebraically a bit, and let's see what we get. So the first step, I'll take this u to the third and I'll throw it on the other side, and we shall have t to the third minus u to the third is equal to, since this has gone on this side, all the remaining terms here have in common t minus u. So let me just pull that in front. T minus u. In fact, let's see, t minus u. Yeah. Well, not yet. Let me t minus u to the third plus, I will group this 3. I will group this 3 terms, 2 u t minus u plus u squared t minus u plus u t minus u squared. I'm just grouping this 3, and from this 3 I'm going to pull out t minus u. So leave the left hand side alone, and we have t minus u to the third plus pulling out a t minus u factor from here, t minus u, and I will have left 2 ut from here plus u squared, plus here I'll have t minus u, only one factor of it. Let me just distribute immediately, and I will have ut plus u squared, or rather, I'm sorry, minus u squared. This plus u squared with this minus u squared cancel out. I'll see what I have left. Meanwhile, t to the third minus u to the third is equal to t minus u to the third plus simply I have 2 ut plus ut, that is 3 ut times t minus u. I'll continue here. Okay, so now what? Now we are going to substitute, let's say, t minus u with x. So let t minus u be equal to x. Then if t minus u is equal to x, then I have this x to the third, then 3 ut would be my number m here, and n would be t to the third minus u to the third, if I'm letting x be equal to t minus u. And then m is equal to 3tu, and n is equal to t to the third minus u to the third. Now, his book, Ars Magna, does not actually represent a derivation of these quantities. As I mentioned before, he rather showed a specific formula for this particular depressed cube. But as I said before, we'll give a general proof here. Okay, now since m is equal to 3tu, then from here u would be equal to m over 3t, and we'll substitute u and substitute u in the formula for n. in n equals to t to the 3 minus u to the 3. So, so we'll have what? We'll have, and so we have the following. We have t to the third minus m to the third over 2 over 2t, over 3t actually. 27, so that's 27 because you are cubing this. You're letting u be equal to m over 3t here, but you are cubing the u, so that will be m to the third times 27t to the 3. And we're saying that is equal to n. Okay, so here we are going to multiply both sides by t to the third, and we rearrange. So multiply by t to the third, both sides obviously, and rearrange. So we'll have t to the 6 minus m to the third over 27 minus n t to the 3 equal to 0. That's what I mean by rearrange. I'm taking this term and throwing that term on the other side. Well, looks like we are going nowhere fast with this, because from something to the power 3, now we're dealing with something to the power 6, which seems more complicated. But what Cardano did at this point, he rewrote t to the 6 as follows. Rewrite. Instead of t to the 6, instead of dealing with now with the equation of the 6th degree, we write in t to the 6 as t to the third to the power 2 minus nt to the 3 minus m to the third over 27 equals to 0. Well, two things. Now, this is an equation of the second degree, and also notice that t to the 3 is the volume of my original cube here. So at this point in time, how to solve a quadratic equation was well known. The formula that we know today was known in some form during Cardano's day as well. So now from something that we don't know how to deal with, something to the power 3, we're dealing with a cubic equation, which was certainly known at that point. So by quadratic formula, we have okay, what is it that we have? We have t to the 3. Okay, this would be your unknown in quadratic formula. T to the 3 would be equal to n plus minus square root of n squared plus 4m to the third over 27, if you do this carefully, over 2. And this is equal to this is equal to n over 2 plus minus 1/2 square root of n squared plus 4m to the third over 27. Okay, you can break this up. This is now the same as n over 2 plus 1/2 square root of, I'm rearranging things inside the square root. This is the same as n to the 2. I want to write n to the 2 as n to the 2 over 4 and actually get rid of this half here, as it would be the same, n to the 2 over 4 plus m to the 3rd over 27. Okay. Now let me continue on. Oops. I will continue in next page, but I'll make sure that we keep the cube here. Okay, so lecture 8, that is page 2. So I'll keep the cube here. So I can refer to it and I'll continue writing. Anyway, so we are here. Since we're dealing with the actual cube, remember t to the 3rd is nothing other than the volume of the entire cube, then we disregard the number here with a minus. So we disregard the case where we're dealing with a minus. This is an actual volume and it cannot possibly have a negative value. So from here we'll say the following. So since we're dealing with the actual cube value, we only take the positive square root. We only take the positive square root. Okay. So we have the following. T to the 3rd equals to n over 2 plus, here we only take the positive value, plus the square root of n to the 2 over 4 plus m to the 3rd over 27. Okay, from here we solve for t. So from here we shall take the cube root of the entire thing. So we take the cube root of the entire thing, n over 2 plus the square root inside of n to the 2 over 4 plus m to the 3 over 27. All right. Now we know the following. What do we know from the substitutions that we did before? Now we know that t to the 3 minus u to the 3 is actually equal to n from here. So this implies that u to the 3 itself is equal to t to the 3 minus n. Okay, so how does that help us? T minus n. So we have u to the 3 is equal to n to the 2 plus square root of n squared over 4 plus m to the 3rd over 27 minus n. I'm just solving for u to the 3rd here, or just substituting what I know. Now this is equal to what? This is equal to minus n over 2 plus the square root of n squared over 4 plus m to the third over 27. So u itself would be again the cube root of this quantity. So finally u is the cube root of minus n over 2 plus the square root of n to the 2 over 4 plus m to the third over 27. Then x itself is t minus u, so finally x itself is equal to what? I do have a formula for u. I know what my t is because we have it from here. So I'll take the, from t, I'm going to minus u. So the cube root of n over 2, this is the t, plus the square root of n to the 2 over 4 plus m to the third over 27, minus again the cube root for u, which is the number we just said. Okay, square root n to the 2 over 4 plus m to the 3 over 27. Alright, so that's basically end of proof. Now it takes a little bit of work for you to actually take this formula and translate it into the words of Cardano. It's exactly the same, it's exactly the very same thing. Okay, well, it should be, a few things should be pointed out here. Mathematicians at that time were not really comfortable, especially since this had a very geometric flavor as a solution. There is no talk here about how to work in general with solutions for a depressed cubic in terms of negative numbers. And it was actually one of the Cardano's contemporaries that stressed out the necessity even for actually imaginary numbers. As you talk about solutions to these equations, of course the imaginary numbers jump in, but at this point in time they were largely ignored, and it was not, as I said before, until one of the Cardano's contemporaries, Raphael Bombelli, that actually showed that the imaginary numbers are rather necessary when it comes to real solutions of the cubic. So translating a real cubic equation into its real solutions. Of course, using imaginary numbers, solutions to such equations were treated in details 2 centuries later by Euler, Cauchy, Gauss, and so on. But besides this, Cardano also gave a solution to the general cubic equation. So he also talked about the solution to ax to the third plus bx to the 2 plus cx plus d equals to 0. So he proposed first that you divide across by the coefficient a, and then whatever is left, let's say you have another cubic. So once you divide by b here, by a, you will have obviously some other number. Let me call it kx squared plus rx plus n equals to 0 once you divide by a. Now, in solving such more general cubic equation, he proposed the following. He made a change of variable. He let x be equal to, or introduce a new variable, let me call it y, variable y, minus b over 3a. So once you substitute x with this other quantity where y is a different or yet another variable, then this equation actually, using this substitution, we rewrite this in the form y to the third plus py equals to q. So if you were to substitute x with this other quantity, then after some rearrangement in algebra, certainly you come to the depressed cubic form which Cardano knew how to solve from before. Again, in his book he gave a specific solution to a very specific general quadratic equation, which succumbed again to his previous recipe of the depressed cube. Nonetheless, it's considered to be yet another great theorem, and as I said before, it's rather interesting to read some more about Cardano. But for the moment, this will be the end of this lecture, and you'll hear from me soon. So long, everyone.